function that determines the length of a string. Well, it turns out we didn't actually need this all along. It turns out that we can get rid of my own custom string length function here. I can definitely delete the whole implementation down here because it turns out in a file called string.h, which is a new header file today, we actually have access to a function called, more succinctly, strlen, S-T-R-L-E-N, which literally does that. This is a function that comes with C, albeit in the string.h header file, and it does pretty much what we just implemented manually. So here's an example of, admittedly, a wheel we just reinvented, but no more. We don't have to do that. And how do you know what kinds of functions exist? Well, let me actually pop out of my browser here to a website that is a CS50's incarnation of what are called manual pages. It turns out that in a lot of systems, Macs and Unix and Linux systems, including the Visual Studio Code instance that we have in the cloud, there are publicly accessible manual pages for functions. They tend to be written very expertly in a way that's not very beginner friendly. So what we have here at manual.cs50.io is CS50's version of manual pages that have this less comfortable mode that give you a sort of cheat sheet of very frequently used helpful functions in C, and we've translated the sort of expert notation to things that a beginner can understand. So for instance, let me go ahead and search for string up at the top here. You'll see that there's documentation for our own getString function, but more interestingly down here, there's a whole bunch of string-related functions that we haven't even seen most of yet, but there's indeed one here called strlen, calculate the length of a string. And so if I actually go to strlen here, I'll see some less comfortable documentation for this function. And the way a manual page typically works, whether in CS50's format or any other system, is you see typically a synopsis of what header files you need to use the function. So you would copy paste these couple of lines here. You see what the prototype is of the function so that you know what its inputs are, if any, and its outputs are, if any. Then down below you might see a description, which in this case is pretty straightforward. This function calculates the length of s. Then you see what the return value is, if any, and you might even see an example like this one that we've whipped up here. So these manual pages, which are again accessible here, and we'll link to these in the problem sets moving forward, are pretty much the place to start when you want to figure out, has a wheel been invented already? Is there a function that might help me solve some problem set problems so that I don't have to really get into the weeds of doing all of those lower level steps as I've had? Sometimes the answer is going to be yes, sometimes it's going to be no. But again, the point of our having just done this together is to reveal that even the functions you start taking for granted, they all reduce to some of these basic building blocks. At the end of the day, this is all that's inside of your computer, is zeros and ones. We're just learning now how to harness those and how to manipulate them ourselves. All right, any questions here on this? Any questions at all? Yeah. Good question. Is it so common that you would have to specify it or not? You do need to include its header files because that's where all of those prototypes are. You don't need to worry about linking it in with -l anything. And in fact, moving forward, you do not ever need to worry about linking in libraries when compiling your code. We, the staff, have configured Make to do all of that for you automatically. We want you to understand that it is doing it, but we'll take care of all of the -ls for you. But the onus is on you for the prototypes and the header files. Other questions on these representations or techniques? Yeah. A good question. If you were to have a string with actual spaces in it, that is multiple words, what would the computer actually do? Well, for this, let me go to ASCIIchart.com, which is just a random website that's my go-to for the first 127 characters of ASCII. This is, in fact, what we had a screenshot of the other day. And if you look here, it's a little non-obvious, but SP is space. If a computer were to store space, it would actually store the decimal number 32, or technically the pattern of zeros and ones that represent the number 32. All of the US English keys that you might type on a keyboard can be represented with a number, and using Unicode, can you express even things like emojis in other languages? Yeah. Good question. Only strings are accompanied by nulls at the end because every other data type we've talked about thus far is of well-defined finite length. 1 byte for char, 4 bytes for ints, and so forth. If we think back to the last week, we did end the week with a couple of problems. Integer overflow is like 4 bytes. Heck, even 8 bytes is sometimes not enough. We also talked about floating point imprecision. Thankfully, in the world of scientific computing and financial computing, there are libraries you can use that draw inspiration from this idea of a string, and they might use 9 bytes for an integer value, or maybe 20 bytes. You can count really high, but they will then start to manage that memory for you. And what they're really probably doing is just grabbing a whole bunch of bytes and somehow remembering how long the sequence of bytes is. That's how these higher level libraries work too. All right, this has been a lot. Let's take one more break here. We'll do like a 7-minute break here, and when we come back, we'll flesh out a few more details. All right. So we just saw strlen as an example of a function that comes in the string library. Let's start to take more of these library functions out for a spin, so we're not relying only on the built-ins that we saw last week. Let me go ahead and switch over to VS Code, and let me create a file called, say, string.h, just to kind of apply this lesson learned as follows. Let me go ahead and include cs50.h, let me include standard.io.h, and this new thing, string.h as well at the top. I'm going to do the usual int main void here. And then in this program, suppose for the sake of discussion that I didn't know about %s for printf, or heck, maybe early on there was no %s format code, and so there was no easy way to print strings. Well, at least if we know that strings are just arrays of characters, we could use %c as a workaround, so to speak, a solution to that sort of contrived problem. So let me ask myself for a string s by using getString here, and I'll ask the user for some inputs. And then let me go ahead and print out, say, outputs, and all I want to do is print back out what the user types. Now, the simplest way to do this, of course, is going to be like last week, printf %s, and plug in the s, and we're done. But again, for the sake of discussion, I forgot about, or someone didn't implement %s, so how else could we do this? Well, in pseudocode, or in English, like what's the gist of how we could solve this problem? Printing out the string s on the screen without using %s. How might we go about solving this? Just in English, high level. What would your pseudocode look like? Yeah. Okay, so just print each letter, and maybe more precisely, like some kind of loop, like let's iterate over all of the characters in s and print one at a time. So how can I do that? Well, for int I gets 0 is kind of the go-to starting point for most loops. I is less than, okay, how long do I want to iterate? Well, it's going to depend on what I type in, but that's why we have strlen now. So iterate up to the length of s, and then increment I with ++ on each iteration, and then let's just print out %c with no new line, because I want everything on the same line, whatever the character is at s bracket I. And then at the very end, I'll give myself that new line just to move the cursor down to the next line so the dollar sign's not in a weird place. All right, so let's see. If I didn't screw up any of the code, make string, enter. So far, so good. String, and let me type in something like hi, enter, and I see output of hi too. Let me do it once more with by, enter, and that works too. Notice I very deliberately and quickly gave myself 2 spaces here and 1 space here just because I literally wanted these things to line up properly, and input is sort of an output, but that was just a deliberate formatting detail. So this code is correct, which is a claim I've made before, but it's not well designed now. It is well designed in that I'm using someone else's library function. Like I've not reinvented a wheel. There's no line 15 or below. I didn't implement string length myself. So I'm at least kind of practicing what I preached. But there's still an imperfection, a suboptimality. This one's really subtle, though. And you have to think about how loops work. What am I doing that's not super efficient? Yeah, in back? Yeah, this is a little subtle, but if you think back to the basic definition of a for loop, and recall when I highlighted things last week, what happens? Well, the first thing is that I gets set to 0, then we check the condition. How do we check the condition? We call strlen on s, we get back an answer like 3 if it's hi exclamation point, and 0 is less than 3, so that's fine, and then we print out the character. Then we increment I from 0 to 1, we recheck the condition. How do I recheck the condition? I call strlen of s, get back the same answer, 3, compare 3 against 1, we're still good, so we print out another character. I gets incremented again, I is now 2, we check the condition. What's the condition? Well, what's the string length of s? It's still 3, 2 is still less than 3. So I keep asking the same question sort of stupidly because the string is presumably never changing in length, and indeed every time I check that condition, that function is going to get called, and every time the answer for hi is going to be 3, 3, 3. So it's a marginal sort of suboptimality, but I could do better, right? Like, don't ask multiple times questions that you can remember the answer to. So how could I remember the answer to this question and ask it just once? How could I remember the answer to this question? Let me say, yeah, back there? So stored in a variable, right? That's been our answer most any time we want to keep something around. So how could I do this? Well, I could do something like this. Int maybe length equals strlen of s. Then I can just change this function call, so to speak. And let me fix my spelling here. Let me fix this to be now comparing against length. And this is now okay, because now strlen is only called once on line 9, and I'm reusing the value of that variable, aka length, again and again and again, so that's more efficient. Turns out that for loops actually let you declare multiple variables at once, so we can actually do this a little more elegantly, all in one line. And this is just now some syntactic improvement. I could actually do something like this. N equals strlen of s. And then I could just say n here, or I could call it length, but heck, well, I'm being succinct, I'm just going to use n for number. So now, it's just a marginal change, but I've now declared 2 variables inside of my loop, I and n. I is set to 0, n is set to the string length of s, but now, hereafter, all of my condition checks are just I less than n, and n is never now changing. All right, so a marginal improvement there. Now that I've used this new function, let's use some other functions that might be of interest. Let me go ahead and write a quick program here that maybe like capitalizes the beginning of, that changes to uppercase some string that the user types in. So let me go ahead and code a file called uppercase.c. Up here I'll use my new friends cs50.h and standard.io and string.h, so standard.io and string.h, so just as before, int main void. And then inside of main, what I'm going to do this time is let's ask the user for a string s using getString, asking them for the before value. And then let me go ahead and just print out something like after, so that just so I can see what the uppercase version thereof is. And then after this, let me go ahead and do the following. For int I equals 0, let's practice that same lesson. So n equals the string length of s, I is less than n, I plus plus. So really nothing new, really, fundamentally yet. How do I now convert characters from lowercase if they are to uppercase? In other words, if I type in hi, hi in lowercase, I want my program now to uppercase everything to capital H, capital I. Well, how can I go about doing this? Well, you might recall that there is this ASCII chart. So let's just consult this real quick. On ASCIIchart.com, we've looked at this last week. Notice that capital A is 65, capital B is 66, capital C is 67, and heck, here's lowercase a, lowercase b, lowercase c, and that's 97, 98, 99. If I actually do some math, there's like a distance of 32, right? So if I'm going to go from uppercase to lowercase, I can do 65 plus 32 will give me 97, and that actually works out across the board for everything else. 66 plus 32 gets me to 98 or lowercase b, or conversely, if you have a lowercase a and its value is 97, subtract 32, and boom, you have capital A. So, all right, there's some arithmetic here involved, but now that we know that strings are just arrays, and we know that characters, which are in those arrays, are just binary representations of numbers, I think we can manipulate a few of these things as follows. Let me go back to my program here and first ask the question, if the current character in the array during this loop is lowercase, let's force it to uppercase. So how am I going to do that? If the character at s bracket I, the current location in the array, is greater than or equal to lowercase a, and s bracket I is less than or equal to lowercase z, kind of a weird Boolean expression, but completely legitimate. Because in this array s is a whole bunch of characters that the humans typed in, because that's what a string is. Greater than or equal to a might be a little nonsensical, because when have you ever compared numbers to letters? But we know from week 0, lowercase a is 97. Lowercase z is, what is it, 1? I don't even remember. What's that? 132, we know, and so that would allow us to answer the question, is the current letter lowercase? All right, so let me go ahead here and answer that question. If it is, what do I want to print out? I don't want to print out the letter itself, I want to print out the letter minus 32, right? Because if it happens to be a lowercase a, 97, 97 minus 32 gives me 65, which is uppercase a. And I know that just from having stared at that chart in the past. Else, if the character is not between little a and big A, I'm just going to print out the character itself by printing s bracket I. And at the very end of this, I'm going to go ahead and print out a new line just to move the cursor to the next line. So again, it's a little wordy, but this loop here, which I borrowed from our code previously, just iterates over the string, aka array, character by character, through its length. This line 11 here, convert characters from lowercase if they are to uppercase. In other words, if I type in hi, hi in lowercase, I want my program now to uppercase everything to capital H, capital I. Well, how can I go about doing this? Well, you might recall that there is this ASCII chart. So let's just consult this real quick. On ASCIIchart.com, we've looked at this last week. Notice that capital A is 65, capital B is 66, capital C is 67, and here's lowercase a, lowercase b, lowercase c, and that's 97, 98, 99. If I actually do some math, there's like a distance of 32, right? So if I'm going to go from uppercase to lowercase, I can do 65 plus 32 will give me 97, and that actually works out across the board for everything else. 66 plus 32 gets me to 98 or lowercase b, or conversely, if you have a lowercase a and its value is 97, subtract 32, and boom.
Okay, so for Scrabble, these already have scores. But they have their own scores as well. So why don't I just say equalizing is easy.
you have capital A. So, all right, there's some arithmetic here involved, but now that we know that strings are just arrays, and we know that characters, which are in those arrays, are just binary representations of numbers, I think we can manipulate a few of these things as follows. Let me go back to my program here and first ask the question, if the current character in the array during this loop is lowercase, let's force it to uppercase. So how am I going to do that? If the character at s bracket I, the current location in the array, is greater than or equal to lowercase a, and s bracket I is less than or equal to lowercase z, kind of a weird Boolean expression, but completely legitimate, because in this array s is a whole bunch of characters that the humans typed in, because that's what a string is. Greater than or equal to a might be a little nonsensical, because when have you ever compared numbers to letters? But we know from week 0, lowercase a is 97. Lowercase z is, what is it, 1? I don't even remember. What is that? 132, we know, and so that would allow us to answer the question, is the current letter lowercase? All right, so let me go ahead here and answer that question. If it is, what do I want to print out? I don't want to print out the letter itself, I want to print out the letter minus 32, right? Because if it happens to be a lowercase a, 97, 97 minus 32 gives me 65, which is uppercase a. And I know that just from having stared at that chart in the past. Else, if the character is not between little a and big A, I'm just going to print out the character itself by printing s bracket I. And at the very end of this, I'm going to go ahead and print out a new line just to move the cursor to the next line. So again, it's a little wordy, but this loop here, which I borrowed from our code previously, just iterates over the string, aka array, character by character, through its length. This line 11 here is just asking the question if that current character, the ith character of s, is greater than or equal to little a and less than or equal to little z, that is between 97 and 132, then we're going to go ahead and force it to uppercase instead. All right, and let me go ahead and zoom out here for just a second. And sorry, I misspoke. 122, which is what you might have said. There's only 26 letters. So 122 is little z. Let me go ahead now and compile and run this program. So make uppercase, /uppercase, and let me type in high and lowercase, enter, and there's the capitalized version thereof. Let me do it again with like my own name in lowercase, and now it's capitalized as well. Well, what could we do to improve this? Well, you know what? Let's stop reinventing wheels. Let's go to the manual pages. So let me go here and search for something like, I don't know, lowercase, and there I go. I did some autocomplete here. Our little search box is saying that, okay, there's an is lower function. Check whether a character is lowercase. Well, how do I use this? Well, let me check. Is lower. Now I see the actual man page for this function. Now we see include ctype.h, so that's the that's the header file I need to include. This is the prototype for is lower. It apparently takes a char as input and returns an int, which is a little weird. I feel like is lower should return true or false. So let's scroll down to the description and return value. It returns, oh, this is interesting, and this is a convention in C. This function returns a non-zero int if C is a lowercase letter, and 0 if C is not a lowercase letter. So it returns non-zero, so like 1, -1, something that's not 0 if C is a lowercase letter, and 0 if it is not a lowercase letter. So how can we use this building block? Let me go back to my code here. Let me add this file, include ctype.h, and down here, let me get rid of this cryptic expression, which was kind of painful to come up with, and just ask this, is lower s bracket I? That should actually work, but why? Well, is lower, again, returns a non-zero value if the letter is lowercase. Well, what does that mean? That means it could return 1, it could return -1, it could return 50 or -50. It's actually not precisely defined. Why? Just because. Like, this was a common convention to use 0 to represent false and use any other value to represent true. And so it turns out that inside of Boolean expressions, if you put a value, like a function call like this, that returns 0, that's going to be equivalent to false. It's like the answer being no, it is not lower. But you can also just in parentheses put the name of the function and its arguments and not compare it against anything, because we could do something like this. Well, if it's not equal to 0, then it must be lowercase, because that's the definition. If it returns a non-zero value, it's lowercase, but a more succinct way to do that is just a bit more like English. If it's is lower, then print out the character minus 32. So this would be the common way of using one of these is functions to check if the answer is true or false. Okay, well, we might be done. Okay. No, so it's not necessarily 1. It would be incorrect to check for 1 or -1 or anything else. You want to check for the opposite of 0, so not equal 0, or more succinctly, like I did by just putting it into parentheses. Let me see what happens here. So this is great, but some of you might have spotted a better solution to this problem a moment ago when we were on the manual pages searching for things related to lowercase. What might be another building block we can employ here? Based on what's on the screen here. Yeah. So to upper, there's a function that would literally do the uppercasing for me, so I don't have to get into the weeds of like -32, +32. I don't have to consult that chart. Someone has solved this problem for me in the past, and let's see if I can actually get back to it. There we go. Let me go ahead now and use this. So instead of doing s bracket I minus 32, let's use a function that someone else wrote and just say to upper s bracket I. And now it's going to do the solution for me. So if I rerun make uppercase and then do slowly dot uppercase, type in high, now it's working as expected. And honestly, if I read the documentation for to upper by actually going back to its man page or manual page, what you'll see is that it says if it's lowercase, it will return the uppercase version thereof. If it's not lowercase, it's already uppercase, it's punctuation, it will just return the original character, which means thanks to this function, I can actually tighten this up significantly, get rid of all of my conditional there, and just print out the to upper return value and leave it to whoever wrote that function to figure out if something's uppercase or lowercase. All right, questions on these kinds of tricks? Again, it all reduces to like week 0 basics, but we're just building these abstractions on top. Yeah. Yes, unfortunately, no. There is no easy way in C to say, give me everything. That was for historically performance reasons. They want you to be explicit as to what you want to include. In other languages like Python, Java, one of which we'll see later this term, you can say, give me everything, but that actually tends to be best practice, because it can actually slow down execution or compilation of your code. Yeah. Does to upper accommodate special characters like punctuation? Yes. If I read the documentation more pedantically, we would see exactly that. It will properly hand me back an exclamation point, even if I passed it in. So if I do make uppercase here, and let me do /uppercase, high with an exclamation point, it's going to handle that too, and just pass it through unchanged. Yeah. Really good question too. No, we do not have access to a function that at least comes with C or comes with CS50's library that will just force the whole thing to uppercase. In C, that's actually easier said than done. In Python, it's trivial. So stay tuned for another language that will let us do exactly that. All right, so what does this leave us with? There's just let's come full circle now to where we began today, where we were talking about those command line arguments. Recall that we talked about RM taking command line argument, the file you want to delete. We talked about Clang taking command line arguments that again modify the behavior of the program. How is it that maybe you and I can start to write programs that actually take command line arguments? Well, here is where I can finally explain why we've been typing int main void for the past week and just asking that you take on faith that it's just the way you do things. Well, by default in C, at least the most recent versions thereof, there's only 2 official ways to write main functions. You might see other formats online, but they're generally not consistent with the current specification. This again was sort of the boilerplate for the simplest function we might write last week, and recall that we've been doing this the whole time, void. What that void means for all of the programs I have written thus far and you have written thus far is that none of our programs that we've written take command line arguments. That's what the void there means. It turns out that main is the way you can specify that your program does, in fact, take command line arguments. That is, words after the command in your terminal window. If you want to actually not use get int or get string, you want the human to be able to say something like hello David and hit enter and just run print hello David on the screen. You can use command line arguments, words after the program name on your command line. So we're going to change this in a moment to be something more verbose, but something that's now a bit more familiar syntactically. If you change that void in main to be this incantation instead, int argc, comma, string argv, open bracket, close bracket, you are now giving yourself access to writing programs that take command line arguments. Argc, which stands for argument count, is going to be an integer that stores how many words the human types at the prompt. The C automatically gives that to you. String argv stands for argument vector. That's going to be an array of all of the words that the human typed at the prompt. So with today's building block of an array, we have the ability now to let the humans type as many words or as few words as they want at the prompt. C is going to automatically put them in an array called argv, and it's going to tell us how many words there are in an int called argc. The int as the return type here we'll come back to in just a moment. Let's actually use now this definition to make maybe just a couple of simple programs, but in problem set 2 will we actually use this to control the behavior of your own code. Let me go ahead and code up a file called argv.0 just to keep it aptly named. Let me go ahead and include cs50.h. Let me go ahead and include, oops, that is not the right name of the program. Let's start that over. Let's go ahead and code up. Void means for all of the programs I have written thus far and you have written thus far is that none of our programs that we've written take command line arguments. That's what the void there means. It turns out that main is the way you can specify that your program does, in fact, take command line arguments. That is, words after the command in your terminal window. If you want to actually not use get int or get string, you want the human to be able to say something like hello David and hit enter and just run print hello David on the screen. You can use command line arguments, words after the program name on your command line. So we're going to change this in a moment to be something more verbose, but something that's now a bit more familiar syntactically. If you change that void in main to be this incantation instead, int argc, comma, string argv, open bracket, close bracket, you are now giving yourself access to writing programs that take command line arguments. Argc, which stands for argument count, is going to be an integer that stores how many words the human typed at the prompt. The C automatically gives that to you. String argv stands for argument vector. That's going to be an array of all of the words that the human typed at the prompt. So with today's building block of an array, we have the ability now to let the humans type as many words or as few words as they want at the prompt. C is going to automatically put them in an array called argv, and it's going to tell us how many words there are in an int called argc. The int as the return type here we'll come back to in just a moment. Let's actually use now this definition to make maybe just a couple of simple programs, but in problem set 2 will we actually use this to control the behavior of your own code. Let me go ahead and code up a file called argv.0 just to keep it aptly named. Let me go ahead and include cs50.h. Let me go ahead and include, oops, that is not the right name of a program. Let's start that over. Let's go ahead and code up argv.c. And here we have include cs50.h, include standard.io.h, int main not void. Let's actually say int argc, string argv, open bracket, close bracket. No numbers in between because you don't know in advance how many words the human's going to type at their prompt. Now let's go ahead and do this. Let's write a very simple program that just says hello David, hello Carter, whoever the name is that gets typed, but not using getString. Let's instead have the human just type their name at the prompt, just like rm, just like clang, just like make, so it's just one and done when you hit enter. No additional prompts. Let me go ahead then and do this. Printf, quote unquote, hello, comma, and instead of world today, I want to print out whatever the human typed in. So let's go ahead and do this. Argv bracket 0 for now, but I don't think this is quite what I want, because of course that's going to literally print out argv bracket 0 bracket. Then I need a placeholder, so let me put a %s here and then put that here. So if argv is an array, but it's an array of strings, then argv bracket 0 is itself a single string. And so it can be plugged into that %s placeholder. Let me go ahead and save my program, and let me go ahead and compile argv. So far, so good. Let me go ahead now and type in my name after the name of the program. So no getString. I'm literally typing an extra word, my own name, at the prompt. Enter. OK, it's apparently a little buggy in a couple of ways. I forgot my \n, but that's not a huge deal. But apparently, inside of argv is literally everything the humans typed in, including the name of the program. So logically, how do I print out hello David or hello so-and-so and not the actual name of the program? What needs to change here? Yeah. Yeah, so presumably index to 1 if that's the second thing I or whichever human has typed at the prompt. So let's do make argv again, /argv enter. Hello null. So this is another form of null, but this is user error now on my part. I didn't do exactly what I said I would. Yeah. Yeah, I forgot the parameter. So that's actually, I should probably deal with that somehow so that people aren't sort of breaking my program and printing out random things like null. But if I do say argv David, now you see hello David. I can get a little curious, like what's at location 2? Well, we can see make argv bracket /argv David, enter. All right, so just nothing is there. But it turns out in a couple weeks we'll start really poking around memory and see if we can't crash programs deliberately, because nothing is technically stopping me from saying, oh, what's at location 2 million, for instance. We could really start to get curious. But for now, we'll do the right thing. But let's now make sure the human has typed in the right number of words. So let's say this. If argc equals 2, that is the name of the program, and one more word after that, go ahead and trust that in argv1 as you proposed is the person's name. Else, let's go ahead and just default here to something simple and basic like, well, if we don't get a name from the user, just say hello world like always. So now we're sort of programming defensively. This time the human, even if they screw up, they don't give us a name or they give us too many names, we're just going to say hello world because I now have some error handling here. Because again, argc is argument count, the number of words total typed at the command line. So make argv, dot/argv. Let me make the same mistake as before. Okay, I don't get this weird null behavior. I get something well-defined. I could now do David. I could do David Malin, but that's not currently supported. I would need to alter my logic to support more than just 2 words after the prompt. So what's the point of this? At the moment, it's just a simple exercise to actually give myself a way of taking user input when they run the program. Because consider, it's just more convenient in this new command line interface world. If you had to use getString every time you compile your code, it'd be kind of annoying, right? You type make, then you might get a prompt. What would you like to make? Then you type in hello or cache or something else. Then you hit enter. It just really slows the process. But in this command line interface world, if you support command line arguments, then you can use these little tricks like scrolling up and down in your history with your arrow keys. You can just type commands more quickly because you can do it all at once, and you don't have to keep prompting the user more pedantically for more and more info. So any questions then on command line arguments, which finally reveals why we had void initially, but what more we can now put in main. That's how you take command line arguments.
Does
Yeah.
it, though?
Yes, if you were to type at the command line something like not a word, but something like the number 42, that would actually be treated as a string. Why? Because, again, context matters. So if your program is currently manipulating memory as though it's characters or strings, whatever those patterns of zeros and ones are, they will be interpreted as ASCII text or Unicode text. If we therefore go to the chart here, that might make you wonder, well, then how do you distinguish numbers from letters in the context of something like chars and strings? Well, notice 65 is A, 97 is A, but also 49 is 1, and 50 is 2. So the designers of ASCII, and then later Unicode, realized, well, wait a minute, if we want to support programs that let you type things that look like numbers, even though they're not technically ints or floats, we need a way in ASCII and Unicode to represent even numbers. So here are your numbers, and it's a little silly that we have numbers representing other numbers, but again, if you're in the world of letters and characters, you got to come up with a mapping for everything. And notice here's the dot. Even if you were to represent 1.23 as a string or as characters, even the dot now is going to be represented as an ASCII character. So again, context here matters. All right, one final example to tease apart what this int is and what it's been doing here for so long. So I'm going to go ahead and add one bit of logic here to a new file that I'm going to call exit.c. So in exit.c, we're going to introduce something that are generally known as exit status. It turns out this is not a feature we've used yet, but it's just useful to know about, especially when automating tests of your own code, when it comes to figuring out if a program succeeded or failed. It turns out that main has one more feature we haven't leveraged, an ability to signal to the user whether something was successful or not. And that's by way of main's return value. So I'm going to go ahead and now modify this program as follows, like this. Suppose I want to write a similar program that requires that the user type a word at the prompt, so that argc has to be 2 for whatever design purpose. If argc does not equal 2, I want to quit out of my program prematurely, because I want to just insist that the user operate the program correctly. So I might give them an error message like missing command line argument \n, but now I want to quit out of the program. Now, how can I do that? The right way, quote unquote, to do that is to return a value from main. Now, it's a little weird because no one called main yet, right? Main just gets called automatically, but the convention is anytime something goes wrong in a program, you should return a non-zero value from main. 1 is fine as a go-to. We don't need to get into the weeds of having many different exit statuses, so to speak, but if you return 1, that is a clue to the system, the Mac, the PC, the cloud device, that something went wrong. Why? Because 1 is not 0. If everything works fine, like let's go ahead and print out hello, comma, %s, like before, quote unquote, argv bracket 1. So this is just a version of the program without an else. So this is the same as doing essentially an else here, like I did earlier. I want to signal to the computer that all is well, and so I return 0. But strictly speaking, if I'm already returning here, I don't technically need, if I really want to be nitpicky, I don't technically need the else, because the only way I'm going to get to line 11 is if I didn't already return. So what's going on here? The only new thing here logically is that for the first time ever, I'm returning a value from main. That's something I could always have done, because main has always been defined by us as taking an int as a return value. By default, main automatically, sort of secretly, returns 0 for you. If you've never once used the return keyword, which you probably haven't in main, it just automatically returns 0, and the system assumes that all went well. But now that we're starting to get a little more sophisticated with our code, and you know the program or something went wrong, you can abort programs early. You can exit out of them by returning some other value besides 0 from main. And this is sort of fortuitous that it's an int, right? 0 means everything worked. Unfortunately, in programming, there are seemingly an infinite number of things that can go wrong. An int gives you 4 billion possible codes that you can use, aka exit statuses, to signify errors. So if you've ever on your Mac or PC gotten some weird pop-up that an error happened, sometimes there's a cryptic number in it. Maybe it's positive, maybe it's negative. It might say error code 123 or -49 or something like that. What you're generally seeing are these exit statuses, these return values from main in a program that someone at Microsoft or Apple or somewhere else wrote. Something went wrong. They are sort of unnecessarily showing you, the user, what the error code is, if only so that when you call customer support or submit a ticket, you can tell them what exit status you encountered, what error code you encountered. All right. Any questions then on exit statuses, which is the last of our new building blocks for now? Any questions at all? Yeah.
God, I don't feel like existing.
No. The question is, can you do things again and again at the command line like you could with getString and getInt, which by default, recall, are automatically designed to keep prompting the user in their own loop until they give you a int or a float or the like. With command line arguments, no. You're going to get an error message, but then you're going to be returned to your prompt, and it's up to you to type it correctly the next time. Good question. Yeah? If you do not return a value explicitly, main will automatically return 0 for you. Like, that is the way C simply works, so it's not strictly necessary. But now that we're starting to return values explicitly, if something goes wrong, it would be good practice to also start returning a value for main when something goes right, and there are no errors, in fact. So let's now get out of the weeds and contextualize this for some actual problems that we'll be solving in the coming days by way of problem set 2 and beyond. So here, for instance, is a problem that you might think back to when you were a kid, the readability of some text or some book, the grade level at which some book is written. If you're a young student, you might read at a first grade level or third grade level in the US, or if you're in college, presumably you're reading at a university level of text. But what does it mean for text, like in a book or in an essay or something like that, to correspond to some kind of grade level? Well, here's a quote, a title of a childhood book: one fish, two fish, red fish, blue fish. What might the grade level be for a book that has words like this? Maybe when you were a kid, or if you have siblings still reading these things, what might the grade level of this thing be? Any guesses? Yeah. Sorry, again? Before grade 1 is in fact correct. So that's for really young kids. And why is that? Well, let's consider these are actually pretty simple phrases, right? One fish, two fish, red. I mean, there's not even verbs in these sentences. They're just nouns and adjectives and very short sentences. And so that might be a heuristic we could use when analyzing text. Well, if the words are kind of short, the sentences are kind of short, everything's very simple, that's probably a very young or early grade level. And so by one formulation, it might indeed be even before grade 1 for someone quite young. How about this? Mr. and Mrs. Dursley of number 4, Privet Drive. We're proud to say that they were perfectly normal. Thank you very much. They were the last people you would expect to be involved in anything strange or mysterious because they just didn't hold with such nonsense. And onward. All right, what grade level is this book at? Okay, I heard 3rd. 7th, 5th, okay, all over the place. But grade 7, according to one particular measure, and whether or not we can debate exactly what age you were when you read this, and maybe you're feeling ahead of your time or behind now. But here, we have a snippet of text. What makes this text assume an older audience, a more mature audience, a higher grade level, would you think? Yeah. Yeah, it's longer, different types of words. There's commas now and phrases and so forth. So there's just some kind of sophistication to this. So it turns out for the upcoming problem set, among the things you'll do is take as input texts like this and analyze them, considering, well, how many words are in the text? How many sentences are in the text? How many letters are in the text? And use those according to a well-defined formula to prescribe what exactly the grade level of some actual text, there's the 3rd, might actually be. Well, what else are we going to do in the coming days? Well, I've alluded to this notion of cryptography in the past, this notion of scrambling information in such a way that you can hide the content of a message from someone who might otherwise intercept it. Right? The earliest form of this might also be when you're younger and you're in class and you're passing a note from one person to another, from yourself to someone else. You don't want to just necessarily write a note in English or some other written language. You might want to scramble it somehow or encrypt it. Maybe you change the A's to a B and the B's to a C so that if the teacher snaps it up and intercepts it, they can't actually understand what it is you've written because it's encrypted. Now, so long as your friend, the recipient of this note, knows how you manipulated it, how you added or subtracted sort of letters to each other, they can decrypt it, which is to say reverse that process. So formally, in the world of cryptography and computer science, this is just another problem to solve. Your input, though, when you have a message you want to send securely, is what's generally known as plain text. There's some algorithm that's going to then encipher or encrypt that information into what's called ciphertext, which is the scrambled version that theoretically can get safely intercepted, and your message has not been spoiled unless that intercept actually knows what algorithm you used inside of this process. So that would be generally known as a cipher. The ciphers typically take, though, not one input, but 2. If, for instance, your cipher is as simple as A becomes B becomes C becomes D, ... Z becomes A, you're essentially adding 1 to every letter and encrypting it. Now, that would be what we call the key. You and the recipient both have to agree, presumably before class in advance, what number you're going to use that day to rotate or change all of these letters by, because when you add 1, they, upon receiving your ciphertext, have to subtract 1 to get back the answer. So, for instance, if the input plain text is high, as before, and the key is 1, the ciphertext using this simple rotational algorithm, otherwise known as a Caesar cipher, might be IJ exclamation point. So it's similar, but it's at least scrambled at first glance. And unless the teacher really cares to figure out what algorithm are they using today or what key are they using today, it's probably sufficiently secure for your purposes. How do you reverse the process? Well, your friend gets this and reverses it by -1. So I becomes H, J becomes I, and things like punctuation remain untouched, at least in this scheme. So let's consider one final example here. If the input to the algorithm is UIJT, XBT, DT50, and the key this time is -1, such that now B should become A, and C should become B, and A should become Z. So we're going in the other direction. How might we analyze this? Well, if we spread all the letters out, and we start from left to right, and we start subtracting one letter, U becomes T, I becomes H, J becomes I, T becomes S, X becomes W, A was D, T. This was CS50. We'll see you next time.
Do I want to do this now or later? How much time do I have left? 37. Terrible. Alright, whatever.
in this lab, your task is going to be to write a program, common letters, a program in. Your program will then prompt for a game of Scrabble letters into x0. It would give me access to the last element. Here in Scrabble.c, you'll notice that after including cs50.h and standardio.h, we have this array of points that has all of the point values for each of the letters of the alphabet in alphabetical order. And then we start by using getString to prompt the user for a word from player 1, storing whatever score function on word 2 will save the result of that 2 to compare score 2 and to print out that it's a tie. A word as input, which is iterating over all of the characters in the word, and for each of those characters, figuring out how many points that character is worth. So in summary, here's what you'll need to do. First, complete the compute score function, returning the number of points that would be given to any particular word. In doing so, you'll want to ignore any non-letter characters. In Scrabble, only the letters A through Z actually count for points. So if the user includes punctuation or spaces inside of the text they write, you should ignore those other characters and only consider the letters when determining the score. Your function should also be case insensitive. That is to say, regardless of whether the character is an uppercase letter or a lowercase letter, you should be able to assign that letter some number of points. Both capital A and lowercase a are each worth 1 point, for example. After you've completed the compute score function, you should then complete the main function by comparing those two values, score 1 and score 2, and then printing either player 1 wins or player 2 wins or tie, depending on how those two scores compare with each other. After you've implemented these steps, you should then be able to run your Scrabble program, provide a word for player 1, and provide a word for player 2, and your program should be able to tell you which of those two words would be worth more in a game of Scrabble. My name is Brian, and this was Scrabble.
Are there like more resources or something? Like, shit. Minutes?
Writing have been written inside of main. They're pretty simple programs. You don't need to have all these branches and things going on. We can just fit it all inside of main, and it doesn't get terribly overwhelming. But as the course goes on, and as you begin to develop programs independently, they're probably going to start to get a lot more than 10 or 15 lines. You might get to hundreds or thousands or tens of thousands of lines of code, and it's really not that crazy a thought. As such, it's probably not a good idea to keep everything inside of main. It can get a little difficult to find what you're looking for if you do that. Fortunately, though, C, and pretty much every other programming language that you might work with, allows us to write functions. And I'm just going to take a quick aside here to mention that functions is one area of computer science, and you'll see many more of them at various points throughout the course and if you continue on, where there's a lot of synonyms for the same word. So we call them functions, but you might also hear them referred to as procedures or methods, particularly if you've ever done any object-oriented programming before, and don't worry if you haven't. Not a big deal, but in object-oriented languages, they're frequently called methods. Sometimes they're called subroutines, but they really all refer to the same basic idea. Let's see what that idea is. What is a function? Well, a function is really nothing more than a black box. A black box that has a set of 0 or more inputs and a single output. So, for example, this might be a function. This is a function called func, and it takes 3 inputs, A, B, and C. And inside that black box, we don't know exactly what it does, but it processes the inputs in some way, and it gives us a single output, in this case, Z. Now, to make it a little less abstract, we could say that maybe we have a function called add that takes 3 inputs, A, B, and C, and processes the output in some way inside the black box to produce a single output. So in this case, if add takes 3, 6, and 7, somewhere inside the add function, we would expect them to be added together to produce the output, which is 3 plus 6 plus 7, or 16. Similarly, you have a function called mult that takes 2 inputs, A and B, processes them in some way such that the output of the function is the product of the 2 inputs. The 2 inputs multiplied together. 4 and 5 being passed into mult, something happens, the output we expect is 20. Why do we call it a black box? Well, if we aren't writing the functions ourselves, which we've done quite a bit so far in CS50, we've seen printf, for example, which is a function that we didn't write ourselves, but we do use all the time. If we aren't writing the functions ourselves, we don't really need to know how it's actually implemented under the hood. So, for example, the black box I just showed you for multiplication. Mult AB could be defined, and this is just in pseudocode, could be defined as output A times B. That makes sense, right? If we have a function called mult that takes 2 inputs, we would expect that the output would be the 2 inputs multiplied together, A times B. But mult can also be implemented like this. We could have a counter variable that gets set inside of mult to 0, and then we repeat this process B times, add A to counter. So, for example, if we multiply 3A
by 5b, we could say set counter to 0, repeat 5 times, add 3 to counter. So we start at 0, and then we do this 5 times. 3, 6, 9, 12, 15. It's the same result. We still get 3 times 5, just the implementation is different. That's what we mean when we say a black box. It just means we don't really care how it's implemented under the hood as long as the output is what we expect. In fact, that's part of the contract of using functions, particularly functions that others write. The behavior is always going to be typical and predictable based on the name of the function. And that's why it's really important when you write functions, or when other people write functions that you might use, that those functions have clear, relatively obvious names and are well documented, which is certainly the case for a function like printf. So why do we use functions? Well, as I said earlier, if we write all of our code inside of main, things can get really cumbersome, really complicated. Functions allow us the ability to organize things and break up a very complicated problem into a lot more manageable subparts. Functions also allow us to simplify the coding process. It's a lot easier to debug a 10-line function versus a 100-line function or a 1,000-line function. If we only have to debug small pieces at a time, or write small pieces at a time, it makes that programming experience a lot better. Trust me on that one. Lastly, if we write functions, we can reuse those various parts. Functions can be recycled, and they can be used in one program or another. You've already written the function. All you need to do is tell that program where to find that function. We've been recycling and using printf for over 40 years. It was only written one time. Pretty useful, right? All right, so functions are great. We know that. Now let's start writing them. Let's start getting them into our programs. In order to do that, the first thing we need to do is declare the function. When you declare a function, what you're basically doing is telling the compiler, hey, just so you know, I am going to be writing a function later on, and here's what it's going to look like. The reason for this is because compilers can do some weird things if they see a set of symbols that they're not familiar with. So we just give the compiler a heads up. I'm creating a function, and it's going to do this. Function declarations generally, if you're organizing your code in a way that others will be able to understand and make use of, you generally want to put all of your function declarations at the very top of your code right before you start writing main even. And conveniently, there's a very standard form that every function declaration follows. They all pretty much look like this. There are 3 parts to a function declaration: return type, name, and argument list. Now, the return type is what kind of variable the function will output. So, for example, if we think back a minute ago to the multiplying 2 numbers function, what do we expect if we multiply an integer by an integer? The output will be probably an integer, right? Multiplying 2 integers together, you get an integer. So the return type of that function would be int. Name is what you want to call your function. This is probably the least important part of the function declaration in terms of functionality, but it's actually probably one of the most important parts of the function declaration in terms of knowing what the function actually does. If you name your function f or g or h or mystery or something like that, you're probably going to get a little tripped up trying to remember what those functions do. So it's important to give your functions meaningful names. Lastly, argument list is the comma-separated list of all the inputs to your function, each of which has a type and a name. So not only do you have to specify what type of variable the function will output, you also want to specify what type and types of variables the function will be accepting as inputs. So let's do an example here. Let's just take a look at a more concrete one. So here's an example of a function declaration for a function that would add 2 integers together. The sum of 2 integers is going to be an integer as well, as we just discussed. And so the return type here in green would be int. That just tells us that add 2 ints is going to, at the end of the day, output or spit back out to us an integer. Given what this function does, we want to give it a meaningful name. Add 2 ints seems appropriate considering we're taking 2 integers as inputs and hopefully adding them together. It might be a bit of a cumbersome name, and frankly, this function is probably not necessary since we have the addition operator, if you recall from our discussion of operators previously. But let's just say for the sake of argument that this function is useful, and so we'll call it add 2 ints. Lastly, this function takes 2 inputs, each of which is an integer. So we have this comma-separated list of inputs. Now, we generally want to give a name to each of them so that they can be used within the function. The names aren't terribly important in this case. We don't necessarily, have any meaning attached to them, so we can just call them A and B. That's totally fine. If, however, you find yourself in a situation where the names of the variables might actually be important, you might want to call them something other than A and B to give them something more symbolically meaningful. But in this case, we don't really know anything else about the function. We just want to add 2 integers, so we'll just call those integers A and B. All right, so that's one example. Why don't you take a second to think about this one? How would we write a function declaration for a function that multiplies 2 floating point numbers? Do you remember what a floating point number is? What would this function declaration look like? I actually recommend that you pause the video here and take, however much time you need, really. Think about what this function declaration would be. What would the return type be? What would the meaningful name be? What would the inputs be? So when you pause the video here and write up a function declaration for a function that would multiply 2 floating point numbers together. All right, hopefully you pause the video. So let's take a look at an example of one possible declaration. Float, mult2 reals, float x, float y. The product of 2 floating point numbers, which recall are how we represent real numbers or numbers with decimal values in C, is going to be a floating point number. When you multiply a decimal by a decimal, you're probably going to get a decimal. You want to give it a relevant name. Multiply 2 reals seems fine, but you can really call it mult2 floats or mult floats, anything like that, as long as it gave some actual meaning to what this black box was going to do. And again, in this case, we don't seem to have any meaning attached to the names of the variables we're passing in, so we can just call them x and y. Now, if you call this something else, that's totally fine. In fact, if you did this declaration instead using doubles instead of floats, if you recall that doubles are a different way to more precisely specify real numbers or floating point variables, that's totally fine too. Either one of those would be fine. In fact, there are several different combinations of ways to declare this function, but these are 2 pretty good ones. All right, so we declared a function. That's great. We told the compiler what it is, what we're going to be doing. Now let's actually write that function. Let's give it a definition so that inside the black box, predictable behavior is happening. And in fact, we are multiplying 2 real numbers together, or adding numbers together, or doing whatever it is that we asked our function to do. So in fact, let's try and define multiply 2 reals, which we just talked about a second ago. Now, the beginning of a function definition looks almost exactly the same as a function declaration. I have both of them here. At the top is the function declaration. Type, name, comma-separated argument list, semicolon. The semicolon indicates that that is a function declaration. The beginning of the function definition looks almost exactly the same. Type, name, comma-separated argument list, no semicolon, open curly brace. The open curly brace, just as we've been doing with main, means that we are now beginning to define what happens inside the black box that we've decided to call mult2 reals. Here's one way to implement it. We could say we declare a new variable of type float called product and assign that variable to the value of x times y, and then return product. What does return mean here? Well, return is the way we indicate that's how we're passing the output back out. So return something is the same as this is the output of the black box. So that's how you do it. Here's another way to implement it. We could just return x times y. X is a float, y is a float, so x times y is also a float. We don't even need to create another variable. So that's a different way to implement the exact same black box. Now take a moment, pause the video again, and try and define add 2 ints, which is the other function we talked about a moment ago. Again, here I put the function declaration, ends with a semicolon, and an open curly brace and a closed curly brace indicate where we will fill in the contents of add 2 ints so that we define the predictable behavior inside the black box. So pause the video and take as much time as you need to try and define an implementation of add 2 ints such that when the function outputs a value, it does in fact return the sum of the 2 inputs. So just like the previous example, there are several different ways that you can implement add 2 ints. Here's one, and here in orange I just had some comments. I just added some comments to indicate what's happening on each line of code. So I declare a variable called sum of type int. I say sum equals a plus b. That's when I'm actually doing the work of adding a and b together, and I return sum. And that makes sense because sum is a variable of type int, right? And what's the data type that this function tells me it's going to output? Int. So I'm returning sum, which is an integer variable, and that makes sense given what we've declared and defined our function to do. Now you can also define the function this way, in sum equals a plus b. Skip that first step, and then return sum. Now you can also implement it this way, which I highly do not recommend. This is bad style for one thing, and really bad design, but it does in fact work. If you take this code, which is in badadder.c, and use it, it actually does add two integers together. It's a very poor implementation of this particular behavior, but it does work. And it's here to illustrate the point that we don't really care what happens inside the black box as long as it has the output that we expect. This is a poorly designed black box, but at the end of the day, it does still output the sum of a plus b. All right, so we've declared functions and we've defined functions, so that's really good. Now let's start to use the functions that we've declared and we defined. To call a function, it's actually pretty easy. All you need to do is pass it appropriate arguments of the data type that it expects, and then assign the return value of that function, assign the return value of that function to something of the correct type. So let's have a look at this in practice in a file called adder1.c, which I have in my CS50 IDE. So here is adder1.c. At the beginning, you see I have my includes, standard.io, and CS50.h, and then I have my function declaration. This is where I'm telling the compiler I'm going to be writing a function called add2ints. It's going to output an integer type variable. That's what this part is right here. And then I have two inputs to it, a and b, each of which is an integer. Inside of main, I ask the user for input by saying give me an integer, and they are prompted to for getInt, which is a function that is included in the CS50 library, and that gets stored in x, an integer variable. Then we prompt them for another integer. We get another integer and store that in y. And then here on line 28 is where we make our function call. We are saying int z equals add2ints x comma y. Do you see why this makes sense? X is an integer type variable, and y is an integer type variable. So that's good. That makes sense with what our function declaration on line 17 looks like. The comma-separated input list expects two integers, a and b. In that case, we can call them whatever we want. It just expects two integers. And x is an integer, and y is an integer. So that works. And we know that function is going to output an integer as well. And so we are storing the output of the function add2ints in an integer type variable, which we're calling z. And then we can say the sum of %i and %i is %i. X, y, and z, respectively, filling in those %i's. What does the definition of add2ints look like? Well, it's pretty simple. It's one of the ones we just saw a second ago. Int sum equals a plus b, return sum. Does this work? Well, let's save the file. And then down here in my terminal, I'm going to make adder1. I'm going to clear my screen. I'm going to zoom in because I know it's a little difficult to see. So we compile this program as adder1, so we can do /adder1. Give me an integer, 10. Give me another integer, 20. The sum of 10 and 20 is 30. So we made a successful function call. Run the function again. -10, 17. The sum of -10 and 17 is 7. This function works. It has the behavior that we expect it to. And so we've made a successful function definition, declaration, and a successful function call. A couple miscellaneous points about functions before we conclude this section. Recall from our discussion of data types previously that functions can sometimes take no inputs. If that's the case, we declare the function as having a void argument list. Do you recall what the most common function we've seen so far that takes a void argument list is? It's main. Recall also that functions sometimes don't actually have an output. In that case, we declare the function as having a void return type. Let's conclude this section by tackling a practice problem. So here's a problem laid out. I want you to write a function called valid triangle. What this function should do is take three real numbers that represent the lengths of the three sides of a triangle as its parameters, or its arguments, or its inputs, another set of synonyms that you might encounter. This function should either output true or false, depending on whether those three lengths are capable of making a triangle. Do you remember the data type that we used to indicate true or false? Now, how do you implement this? Well, no, there are a couple of rules regarding triangles that are actually useful to know. A triangle can only have sides with positive length. That makes sense. You're probably saying duh. The other thing to note, though, is that the sum of the lengths of any two sides of the triangle has to be greater than the length of the third side. That's actually true. You can't have a triangle of sides 1, 2, and 4, for example, because 1 plus 2 is not greater than 4. So those are the rules that determine whether or not the three inputs can conceivably form a triangle. So take a couple of minutes and declare and then define this function called valid triangle, such that it actually has the behavior specified here. It will output true if those three sides are capable of comprising a triangle, and false otherwise. Ready to see how you did? Here's one implementation of valid triangle. It's not the only one. Yours might vary slightly, but this one does in fact have the behavior that we expect. We declare our function at the very top, bool valid triangle, float x, float y, float z. So again, this function takes three real numbers as its arguments, floating point value variables, and outputs a true or false value, which is a boolean, recall. So that's why the return type is bool. Then we define the function. First thing we do is check to make sure that all of the sides are positive. If x is less than or equal to 0, or if y is less than or equal to 0, or if z is less than or equal to 0, that can't possibly be a triangle. They don't have positive sides, and so we can return false in that situation. Next, we check to make sure that every pair of inputs is greater than the third one. So if x plus y is less than or equal to z, or if x plus z is less than or equal to y, or if y plus z is less than or equal to x, that also can't be a valid triangle. So we return false again. Assuming we passed both of the checks, though, then we can return true, because those three sides are capable of creating a valid triangle. And that's it. You've now declared and defined, and you may be able to now use and call this function. Great job. I'm Doug Lloyd. This is CS50. Accessed. There are two primary scopes in C, local variables and global variables. Now, local variables can only be accessed within the functions in which they're created. They can't be accessed by every other function that exists in your program, only the function in which it was created. Global variables, on the other hand, can be accessed by any function in the program. And the reason for that is because they're not created inside of any particular function. We declare them outside of all of the functions, which means that every function knows where it is and can access and manipulate it. So far in the course, you've pretty much been working exclusively with local variables. Here's an example of a very, very simple main function and a very simple additional function that we've written.
Why is it below? You're using it and then it's below. I don't understand that. Is that how C
In this case, x, which I colored green just to highlight the locality or the scope of that variable, is local to the function triple. Main cannot refer to x at all. It doesn't know what it is. No other function, in fact, if we had additional functions in here, could refer to x. Similarly, result, which I colored blue, is local only to main. Only main knows what the variable result is. Triple cannot use it. Now, as I mentioned, global variables do exist. If you declare that variable outside of any function, all of the functions in the program can refer to it. So in this case, I've highlighted in green a global variable declaration. In this case, the variable being declared is called global, to be extremely clear about it. It is a type float, and I assign it the value 0.5050. You'll notice that in main and in triple, I am able to refer to global. And in fact, if I go through the program as indicated, main first calls triple, triple multiplies global by 3, which sets its value to 1.5 something, 1.51 or something like that. And then main also prints out the value of global. So main will not print out 0.5050, it will print out global times 3, 1.51. So you gotta be careful when you're working with global variables. While they're very flexible in being able to pass information around so that every function can use it, it also can have some dangerous consequences if one function changes the value of a variable before you expect it to be changed. Why does this distinction matter? Why do we care whether some variables are local and others are global? Well, for the most part, local variables in C are what's called passed by value when we make a function call. What does that mean? Well, when a variable is passed by value, the call E, which is another way of saying the function that is receiving the variable that gets passed in as an input, it actually doesn't receive that variable itself. It receives its own copy of it to work with. This is a really important distinction. We just saw a second ago that with global variables, if we manipulate the global variable in one function, its effect is the effect in that one function carries through to every other function. But with local variables, that's not true. Each function, when it receives variables as input, receives copies of those variables, not the variables themselves. So what is the side effect of that? That means that the variable in the caller, the function that is making the function call, is unchanged unless you overwrite it. For example, in this code, foo is not changed at all. In foo equals 4, call triple of foo. Inside of triple, we would expect that foo would be multiplied by 3 in return, but there's actually no effect. Here, though, a very subtle difference. This does have the effect we want. Do you see why? We're overwriting foo in main this time. So in foo equals 4, foo equals triple foo. When we make that call, triple gets its own copy of foo, its own copy of 4. It says return 4 times 3, or whatever variable gets passed in times 3. And then we assign the return value of triple to foo again. So this actually would overwrite foo. This is the only way to do this with local variables. So now, if we add another line of code here at the end of main to print out the value of foo, it would in fact print out 12. Variable scope is generally not too much of a problem if you name all of your variables different things, but it can get kind of nasty if the same variable name appears in multiple functions, which will happen a lot if you ever do work in the real world, where you are working on collaborative programs and people in different teams are working together to write the same program or the same set of programs. They'll frequently reuse variable names, particularly common ones like x, y, I, j, and so on. But when variables have the same name, scope issues can get a little trickier to parse. For example, do you know what will be printed out at the end of this particular program? Take a minute, pause the video, and read through this program. You can see at the top we have a function declaration for a function called increment. That function takes a single parameter, an integer, which we call x, and it outputs an integer. That's the return type at the beginning. Then we have main, a couple of lines of code in main, the last of which is a print statement. And remember, that's the question here. What is actually going to be printed at the end of this function? And then we actually have the definition of increment below. So take a minute, step through the code, trace things out. Do you know what will be printed at the end of this particular program?
Take a minute. Okay, taking a minute. Int increment int x. Int main void. Int x equals 1, int y. Y equals increment x. Okay, and which was 1. Printf x is, I don't know what percent I is, y is percent I, x and y, but it doesn't ask what x and y is, because we have it above. Y is increment x. What? Is that a function? I don't know. No, the function is down below. Int increment x into x. X increases by 1, so it just increases by 1. So printf x is, y is. So y is always going to be greater than x by 1, right? So that's what it is. It's just giving you x and then y.
All right, hopefully you've taken a few seconds to try and parse this one out. Let's do it together. So I crossed out increment declaration at the top there. It was kind of a distraction. It's not its own variable. It doesn't have its own scope. It's just a function declaration. So for purposes of trying to parse out what's happening in this program, we might as well just avoid it. Now, we have in this case, the reason the problem is tricky is because we have local variables in both main and increment, each of which is called x. And of course, the crux of this issue is trying to suss out which x gets changed and how does it get changed. So I've colored every instance of x that's local to main, red. And I've colored every instance of x that's local to increment, blue. Notice in that third line of main, y equals increment x, the increment is not being passed main's x, or the red x. It's getting passed a copy of it. And it's only going to work with that copy of it, the blue x. If you're mathematically inclined, you might have instead thought of this as x sub m for main and x sub I for increment, but it's the same idea. X sub m, or the red x's in the previous slide, are the variables that are local, is the instance of x rather that is local to main, and x sub I, or the blue variables in the previous slide, are the instances of x that are local to increment. So, were you able to figure out what this function printed at the end? I'm Doug Lloyd, and this is CS50.
Yeah. Okay, so I'm not a complete idiot. Maybe. Debatable. Of course. Just watch all the videos because I don't want to do any work.
Game, there's a certain spirit elementary school game where you would guess a number and someone would tell you it's right or wrong. And I called my program guess. So I can run it in the terminal with /guess. Here I do /guess, hit enter, and I have to guess a number. So here I might guess maybe 2 and hit enter, but then I get this flood of messages in the terminal. I'm wondering, well, what's wrong with this? Why am I getting so many messages here? And to try to figure that out, I can go into my code with code guess.c. And then I can see, well, I'm not entirely sure what might be wrong here. So I need to pause my code at some point. And for that, I can use a breakpoint. So let me go ahead and go to this left side of my guess.c file where I see these red sort of circles pop up. I can click on one of them to turn it bright red. And at that point, I set a pause point in my code. I can use debug50 to go in and actually step through my code and see what's going on in there. So let me go ahead and type debug 50 of guess, hit enter. So now that I have my code opened up in debug 50, I can see a few different things. I can see that my number variable is currently set to 0, and my guess is currently set to this odd 32,764. But as I go through my code, I'll actually see those numbers sort of fall into place. So if I use this step over button, sort of walk to the next line of my code, I can see that number becomes 5, as I expect it to on line 6. And then as I go to line 8 and step over that, I get prompted for what's my guess. And at that point, I might type, well, 3 again, and I'll hit enter. And I see guess becomes 3. So now I'm wondering, well, if my guess is wrong, and my number is 5, my guess is 3, shouldn't I only get wrong guess just once? So I'll actually just keep walking through my code, step over, and I'll see I'm printing wrong guess, which seems right. And now I should just exit the program, that should be it. But I really see that my line in that yellow highlight is going back up to 10, line 10 there, and it's actually continuing to go through and print wrong guess. And so at this point, I can actually see that maybe the bug in my code is I shouldn't have used a while loop. I should have maybe used an if statement where I'm only checking for this condition once. So now that my while loop has changed to an if statement, I should be able to recompile my code and see what's changed. So I can use make guess, and then I'll run my code, guess. And when I guess 3, I guess I should get wrong guess. So I'll do 3, and then I'll get wrong guess, but also you're correct. And at this point, there's probably another bug in my code, and so I'll actually leave this one up to you to use debug 50 and see, well, why am I getting both wrong guess and you're correct?
What the fuck?
To help figure out what's wrong with it. So here, I'm trying to write a guessing game. There's sort of a spirit elementary school game where you would guess a number and someone would tell you it's right or wrong. And I called my program guess. So I can run it in the terminal with ./guess. Here I do ./guess, hit enter, and I have to guess a number. So here I might guess maybe 2 and hit enter, but then I get this flood of messages in the terminal. I'm wondering, well, what's wrong with this? Why am I getting so many messages here? And to try to figure that out, I can go into my code with code guess.c. And then I can see, well, I'm not entirely sure what might be wrong here. So I'm going to pause my code at some point. And for that, I can use a breakpoint. So let me go ahead and go to this left side of my guess.c file where I see these red sort of circles pop up. And I can click on one of them to turn it bright red. And at that point, I've set a pause point in my code, and I can use debug 50 to go in and actually step through my code and see what's going on in there. So let me go ahead and type debug 50 of guess, hit enter. So now that I have my code opened up in debug 50, I can see a few different things. I can see that my number variable is currently set to 0, and my guess is currently set to this odd 32,764. But as I go through my code, I'll actually see those numbers sort of fall into place. So if I use this step over button to sort of walk to the next line of my code, I can see that number becomes 5, as I expect it to on line 6. And then as I go to line 8 and step over that, I get prompted for what's my guess. And at that point, I might type, well, 3 again, and I'll hit enter. And then I see guess becomes 3. So now I'm wondering, well, if my guess is wrong, and my number is 5, my guess is 3, shouldn't I only get wrong guess just once? So I'll actually just keep walking through my code with step over, and I'll see I'm printing wrong guess, which seems right. And now I should just exit the program. That should be it. But I really see that my line in that yellow highlight is going back up to 10, line 10 there. And it's actually continuing to go through and print wrong guess. And so at this point, I can actually see that maybe the bug in my code is I shouldn't have used a while loop. I should have maybe used an if statement where I'm only checking for this condition once. So now that my while loop has changed to an if statement, I should be able to recompile my code and see what's changed. So I can use make guess, and then I'll run my code, guess. And when I guess 3, I guess I should get wrong guess. So I'll do 3, and then I'll get wrong guess, but also you're correct. And at this point, there's probably another bug in my code, and so I'll actually leave this one up to you to use debug 50 and see, well, why am I getting both wrong guess and you're correct?
It's because it's under the same if statement. You need to put in if else, and then put in the parameter easy. 10 minutes.
Names flying around our code. In this case, arrays are going to come in really handy. Arrays are a really fundamental data structure for any programming language that you will use, and they're really, really useful, particularly as we'll see in CS50. We use arrays to hold values of the same data type at contiguous memory locations. That is to say, it's a way that we can group a bunch of integers together in memory or a bunch of characters or floats in memory really close together and work with them without having to give each one its own unique name, which can get cumbersome after a little while. Now, one way to analogize arrays is to think about your local post office for a second. So step away from programming and just close your eyes and visualize in your mind your local post office. Usually, in most post offices, there's a large bank of post office boxes on the wall. An array is a giant block of contiguous memory, the same way that a mail bank in your post office is a large space on the wall of the post office. Arrays have been partitioned into small, identically sized blocks of space, each of which is called an element, in the same way that the wall at the post office has been partitioned into small, identically sized blocks of space, which we call a P.O. box. Each element of the array can store a certain amount of data, just as each post office box is able to hold a certain amount of mail. What can be stored in each element of the array is variables of the same data type, such as int or char. Just like in your post office box, you can only fit things of a similar type, such as letters or small packages. Lastly, we can access each element of the array directly by index number, just as we can access our post office box by knowing its mailbox number. Hopefully that analogy helps helps you get your head around the idea of arrays by analogizing with something else that you are probably already familiar with. In C, the elements of an array are indexed starting from 0, not from 1, and this is really important. In fact, this is why we in CS50 and why computer scientists frequently will count from 0. It's because of C's array indexing, which always starts at 0. So if an array consists of n elements, the first element of that array is located at index 0, and the last element of the array is located at index n minus 1. Again, if there's n elements in our array, the last index is n minus 1. So if our array has 50 elements, the first element is located at index 0, and the last element is located at index 49. Unfortunately, or fortunately, depending on your perspective, C is very lenient here. It will not prevent you from going out of bounds of your array. You can access the -3 element of your array or the 59th element of your array if your array only has 50 elements. It won't stop you from your program from compiling, but at runtime you might encounter a dreaded segmentation fault if you start to access memory that is outside the bounds of what you asked your program to give you. So do be careful. What does an array declaration look like? How do we code an array into existence like we code any other variable? There are 3 parts to an array declaration: a type, a name, and a size. This is very similar to a variable declaration, which is just a type and a name. The size element being the special case for an array because you're getting a bunch of them at the same time. So the type is what kind of variable you want each element of the array to be. Do you want it to be an array of integers? Then your data type should be int. Do you want it to be an array of doubles or floats? Data type should be double or float. The name is what you want to call your array. What do you want to name this giant bank of integers or floats or chars or doubles or whatever have you? What do you want to call it? Pretty self-explanatory. Lastly, size, which goes inside of square brackets, is how many elements you would like your array to contain. How many integers do you want? How many floats do you want? So for example, int student grades 40. This declares an array called student grades, which consists of 40 integers. Pretty self-explanatory, I hope. Here's another example. Double menu prices 8. This creates an array called menu prices, which consists of room in memory for 8 doubles. If you think of every element of an array of type data type, so for example, if a single element of an array of type int, the same way you would think of any other variable of type int, all the familiar operations that we discussed previously in the operations video will make sense. So here we could declare an array of booleans called truth table, which consists of room for 10 booleans. And then just like we could assign a value to any other variable of type boolean, we could say something like truth table square bracket 2, which is how we indicate which element of the truth table? The third element of the truth table. Remember, we're counting from 0. So that's how we indicate the third element of the truth table. Truth table 2 equals false. Just like we could declare, or we could assign rather any boolean type variable to be false. We can also use it in conditions. If truth table 7 equals true, which is to say if the 8th element of truth table is true, maybe we want to print a message to the user, printf true. Now I can also just say truth table 10 equals true, right? Well, I can, but it's pretty dangerous because remember, we have an array of 10 booleans. So the highest index that the compiler has given us is 9. This program will compile, but if something else in memory exists where we would expect truth table 10 to go, we could suffer a segmentation fault. We might get away with it, but in general, pretty dangerous. So what I'm doing here is legal C, but not necessarily the best move. Now, when you declare and initialize an array simultaneously, there's actually a pretty special syntax that you can use to fill up the array with its starting values. It can get kind of cumbersome to declare an array of size 100 and then have to say element 0 equals this, element 1 equals this, element 2 equals that. What's the point, right? If it's a small array, you can do something like this. Bool truth table 3 equals open curly brace, and then comma separate the list of elements that you want to put in the array. Then close curly brace, semicolon. This creates an array of size 3 called truth table with elements false, true, and true. And in fact, the instantiation syntax I have here is exactly the same as doing the individual element syntax below. These two ways of coding would produce the exact same array. Similarly, we could iterate over all the elements of an array using a loop, which in fact is a very strongly recommended at-home exercise. How do you create an array of 100 integers where every element of the array is its index? So for example, we have an array of 100 integers, and the first element we want to put 0, and the second element we want to put 1, and the third element we want to put 2, and so on and so on. That's a really good at-home exercise to do that. Here, doesn't look like too much has changed, but notice that in between the square brackets this time, I've actually omitted the number. If you're using this very special instantiation syntax to create an array, you actually don't need to indicate the size of the array beforehand. The compiler is smart enough to know that you actually want an array of size 3 because you put 3 elements to the right of the equal sign. If you put 4, it would have given you a truth table of size 4, and so on and so on. Arrays are not restricted to a single dimension, which is pretty cool. You can actually have as many size specifiers as you wish. So for example, if you want to create a board for the game Battleship, which if you've ever played is a game that's played with pegs on a 10 by 10 grid, you could create an array like this. You could say bool Battleship square bracket 10 close square bracket 10 close square bracket. And then you can choose to interpret this in your mind as a 10 by 10 grid of cells. Now in fact in memory it really does just remain a 100 element single dimensional array. And this in fact goes for if you have 3 dimensions or 4 or 5, it really just does become multiply all of the indices or all of the size specifiers together and you just get a one-dimensional array of that size. But in terms of organization and visualization and human perception, it can be a lot easier to work with a grid if you're working on a game like Tic-Tac-Toe or Battleship or something like that. It's a great abstraction instead of having to think about a tic-tac-toe board as a line of 9 squares or a Battleship board as a line of 100 squares. A 10 by 10 grid or 3 by 3 grid is probably a lot more easy to perceive. Now, something really important about arrays. We can treat each individual element of the array as a variable. We saw that earlier when we were assigning the value true to certain booleans or testing them in conditionals. But we can't treat entire arrays themselves as variables. We cannot, for example, assign one array to another array using the assignment operator. It's not legal C. If we want to, for example, what we would be doing in that example would be to copy one array into another. If we want to do that, we actually need to use a loop to copy over each individual element one at a time. I know it's a little time consuming. So for example, if we had this line of code, or these couple lines of code, would this work? Well, no, it wouldn't, right? Because we're trying to assign foo to bar. That's not going to work because it's an array, and we just described that that's not legal C. Instead, if we want to copy the contents of foo into bar, which is what we're trying to do here, we would need a syntax like this. We have a for loop that goes from j is equal to 0 up to 5, and we increment j on every iteration of the loop and assign elements like that. This would result in bar also being 1, 2, 3, 4, 5, but we have to do it this very slow element by element way instead of by just copying the entire array. In other programming languages, more modern ones, you can in fact do just that simple equals syntax, but C, unfortunately, we're not allowed to do that. Now, there's one other thing I want to mention about arrays that can be a little bit tricky the first time you work with them. We discussed in a video about variable scope that most variables in C, when you call them in functions, are passed by value. Do you remember what it means to pass something by value? It means we're making a copy of the variable that's being passed in. The callee function, the function that's receiving the variable, doesn't get the variable itself. It gets its own local copy of it to work with. Arrays, of course, do not follow this rule. Rather, what we call this is passing by reference. The callee actually does receive the array. It does not receive its own local copy of it. And if you think about it, this kind of makes sense. If arrays are really large, it takes so much time and effort to make a copy of an array of 100 or 1,000 or 10,000 elements that it's not worth it for a function to receive a copy of it, do some work with it, and then just kind of be done with the copy. It doesn't need to have it hanging around anymore. Because arrays are so bulky and cumbersome, we just pass them by reference. We just trust that function to don't break anything. So it does actually get the array. It doesn't get its own local copy of it. So what does this mean then when the callee manipulates elements of the array? What happens? For now, we'll gloss over why exactly this happens, why arrays are passed by reference and everything else is passed by value. But I promise you, we will return and give you the answer to this in a later video. Here's one more exercise for you before we wrap up things on arrays. There's a bunch of code here that's not particularly good style. I'll make that caveat. There's no comments in here, which is pretty bad form, but it's only because I want to be able to fit everything on the screen. At the top, you can see that I have two function declarations for set array and set int. Set array apparently takes an array of 4 integers as its input, and set int apparently takes a single integer as its input, but both of them don't have an output. They output. The return type of each one is void. In main, we have a couple of lines of code. We declare an integer variable called a and assign it value 10. We declare an array of 4 integers called b and assign the elements 0, 1, 2, and 3 respectively. Then we have a call to set int and a call to set array. The definitions of set array and set int are down below at the bottom. And so again, I ask you the question, what gets printed out here at the end of main?
Okay, what gets printed out? Alright, void set array, int array 4, array 0 is 22. What? Array 0, int array 4, array 0. What? Okay. Why are we changing it to 22? Void set in x equals 22. So, huh? Printf something and then new line. A, B, 0, 22. What is A? Set int A. Int A, 10. 10 and 22? What the hell? Why is this useful?
This is a printf call. I'm printing out two integers. I'm printing out the contents of A and the contents of B square bracket 0. Pause the video here and take a minute. Can you figure out what this function will print at the end? Hopefully, if you recall the distinction between passing by value and passing by reference, this problem wasn't too tricky for you. And the answer you would have found is this. If you're not really sure
What? Yeah, but what?
as to why that's the case, take a second, go back, review what I was just discussing about passing arrays by reference versus passing other variables by value, and hopefully it'll make a little bit more sense. I'm Doug Lloyd, and this is CS50.
This is not helpful. What the hell? How is this helpful? Maybe it's helpful. I'm just too stupid to figure it out. How long is this video? Alright. 3 minutes. 4 minutes.
Probably started like this: int main void. We've been collecting user input if we need it in our program, such as the Mario program, for example, by in-program prompts. We haven't needed to modify the declaration of main because instead, inside of main, we just say, you may call to get int. How large do you want the pyramid to be? Or you may call to get float. How much change should I output to the user? There is another way, though. And if we want our users to be able to provide data to our program at runtime instead of while the program is running, a subtle distinction, but sometimes a very useful one, we need a new form of declaring main. We can't use int main void if we want to collect other data at the command line when the user runs their program, hence command line arguments. To collect these command line arguments from the user, change your declaration of main to look like this: int main, open paren, int argc, comma, string argv, square brackets, and then open curly brace. So what does that mean already? Well, we are passing in two parameters or arguments or inputs to main. One, an integer called argc, and the other is what? It's an array.
It's an array of all of the inputs. It's the words that are entered.
Array of strings, right? You see that square bracket notation. It's an array of strings. It's not an individual string. It's an array of strings. And these two arguments, argc and argv, enable you to know what data the user has provided at the command line and how many things they provided at the command line. Pretty useful things to work with. Argc stands for argument count. And you should know, by the way, that you could call argc whatever you wanted. You can call argv whatever you wanted. These are just conventional names that we use for them: argument count, and as we'll see in a second, argument vector, argv. But you don't have to call them argc and argv if you don't want to, but conventionally, that's what we do. So anyway, argc, the argument count. It's an integer type variable, and so as you might expect, if we have two things that we're going to be finding out, what the user typed and how much stuff the user typed, argc is going to tell us how much stuff the user typed. So it gives you a number of command line arguments the user typed when the program is executed. So if your program is run /greedy, and inside of your greedy program, your main function has the declaration int main, int argc, string argv, square brackets, then argc in that case is 1. Now notice we don't count how many things the user typed after the program name. The program name itself counts as a command line argument. So /greedy, in that case, argc is 1. If the user typed /greedy 1024 CS50 at the command line, argc in that case would be 3. And we know this because the way that the division between the strings is detected is whether there's a space or a tab or something like that between them. So any amount of white space, so-called, between the values typed at the command line indicates how many there are. So /greedy space 1024 space CS50, argc in that case is 3. Argv is the argument vector. Vector, by the way, is just another word for an array. And this is an array that stores strings, one string per element, which is the strings that the user actually typed at the command line when the program is executed. Now, as is the case with any array, if you recall from our discussion of arrays, the first element of argv is always going to be found at argv square bracket 0. That's the first index of the argv array. So that will always, and in fact, that will always be the name of the program. Will always be located at argv square bracket 0. The last element of argv is always found at argv square brackets argc minus 1. Do you see why? Remember how many
in the array, the total number of characters minus 1. Well, I don't know what it does. Minus what? If it's 10, there's 10 characters minus 1. Oh, because 0 is number 1. Got it.
Elements exist in this array? Well, we know that. It's argc number of elements. If the user typed 3 things at the command line, argc is 3. But because in C, when we're working with arrays, each element of the array, or rather the indices of the array, start at 0. If we have 3 elements in our array, we have an element at argv0, an element at argv1, and an element at argv2. There is no element at argv3 in an array of size 3. So that's why the last element of argv can always be found at argv square brackets argc minus 1. So let's assume the user executes the greedy program as follows. If they type the command line /greedy space 1024 space CS50. And for whatever reason, we've already prepared our greedy program to know and work with these command line arguments. We didn't previously when we worked on it for the greedy problem, but let's say we've now modified it so that we do process the command line arguments in some way. In this case, argv0 is /greedy. What's argv1? Well, it's 1024, right? It is 1024, but here's a really important distinction. Do you remember the data type of argv? It stores strings, right? But it looks like 1024 is an integer value. This is a really important distinction and is actually going to become something that you might encounter in later problems. Everything in argv is stored as a string. So argv1's contents are the string 1024, consisting of those 4 characters. It's as if the user typed 1024 as individual letters or characters. It is not the integer 1024, and so you can't directly work with it by saying, int 1000, or rather int x equals argv1 minus 24. Intuitively, you might think of that as, okay, well, it's 1024 minus 24, so x is equal to 1000. But in fact, that's not the case because argv1 is a string, the string 1024. Now, there is a function that can be used to convert strings to integers. I won't spoil it for you now, but I'm sure Zamilo will be happy to tell you about it in the walkthrough for a future problem. But you can also find functions that would do this in reference 50. If you go to the reference guide, you can find a function that will make this conversion for you. But again, in the walkthrough for a future problem, Zamilo will be happy to tell you what function it is that will convert the string 1024 to the integer 1024. All right, so moving on. We've covered argv0. We covered argv1. What's in argv2? CS50. That one's probably pretty self-explanatory. What's in argv3? Well, again, we don't really know, right? We have an array of size 3. That's how many elements the user typed in the command line. So if we go to argv3, we're now overstepping the bounds of our array. The compiler will let us do this. There's no intuitive problem with it. But in terms of actually what's going to happen, we don't really know. It depends on what is located at the memory where argv3 would be expected to be. And so we could end up getting away scot-free. More likely than not, particularly when we're working with argv as opposed to any other array that's in our program, we're probably going to suffer a segmentation fault. So again, be sure not to overstep the bounds of your arrays, particularly argv, given its high degree of importance in your programs. I'm Doug Lloyd. This is CS50.
Okay. I watched all of the labs. That was actually pretty helpful. No progress on the homework. We'll try again tomorrow. Thanks for watching. Goodbye.